I'm very grateful to colleagues at the Eli and Lili Safra Center for extending this amazing honor and pleasure for me to give the Heller lecture. So as Leon mentioned, I'm interested in human cognition, and I use human neuroscience methods to understand human cognition. And I'm respectful of the boundaries and limitations of the methodology I use. So unlike many of the work that some of you do at the circuit level or cellular level, at the molecular level, I believe that the human neuroscience methods, which change on an almost weekly basis these days, are becoming amazing and ever more powerful, still nevertheless are most useful for trying to lift out of our cognition some of the principles of cognitive systems. So these are sort of high-level conceptual questions that I'm interested in and that I think the methods enable us to address in the field. Of course, sometimes we also can get glimpses of the neural systems that are involved in supporting some cognitive functions and also some of the dynamics of these systems. But I think that our methods become quite limited when we're trying to get to much more granular, mechanistic kinds of explanations. But hopefully, these kind of conceptual breakthroughs help frame some of the work in other levels of observation. In my own sort of experience, sometimes as editor in different big journals, I sense that sometimes there are some sorts of snobberisms from the molecular people looking up to the flaky cognitive people, and some of the cognitive people who pity the molecular and cellular people for being lost in soup. And I think the game is really about all of us working together to sort of recognize the richness of behavior all the way to the richness of the amazing, crazy mechanisms at all different levels that support that. So my work, therefore, will remain kind of at this kind of, I would say, high level of description. In particular, I'm going to continue the conversation that I started the other day on principles of primarily memory and attention, but through sort of perception and a bit of action, but not much action, Elon. So I'm going to start exactly where I started last time, just for the benefit of those who weren't here, but then the talks will eventually become different, I promise you. So when we think of memory and attention, we tend to think about memory as being about the past. And if we look back at the original empirical descriptions, we can see that memory is really very much about the past. So from Ebbinghaus, we get this kind of quote of memories being mental states of every kind which were at one time present in consciousness and then have disappeared. And if I were to be honest, I would say that the field of memory is still kind of stuck in emphasizing these backward-looking functions of memory. Of course, there's also a lot of work looking at how memories and learning change adaptive behavior and action, but there's less emphasis on how memories actually change the initial pickup of the world and perception, which is something that I'll talk about today. Then when we think of attention, we think of attention as forward-looking, attention as being about anticipation, and as William James, as usual, very eloquently put, he talks about this notion of organic adjustment or ideational preparation or pre-perception, so preparation of things to come. And as I started last Tuesday, my aim really is to sort of put memory and attention working together much more intimately in what I like to think of as a back and forth in order to guide adaptive behavior. So the big headline, the big conceptual point is that memory and attention work together, linking past and future to guide adaptive behavior. And in this framework, we can think of the traces left behind by experience, or these memories, so these traces as being the essence of memories, which can be very, very brief and iconic, sort of still kind of part of our rearward part of our perception, to short-term memory, or what I'm going to call working memory, further back, including some remote long-term memories. And it is, through these traces that are able to facilitate perception by these functions, which I call attention. So in my way of thinking, attention is very much about functions and not about states of being. So they're about this prioritization and selection of relevant information. And on Tuesday, we talked about how normally people think about attention as working forward to influence perception, but on Tuesday we also saw how attention, how these functions of prioritization and selection can also work within memory traces. We talked a lot about working memory traces, and we're now looking into long-term memory traces, so that these can also, their relevant parts can then come and feed forward to change perception. So if we were to start thinking about how our perceptual or mental experience comes about, and we open a typical textbook, or if we just ask the intelligent person on the street, we think of the brain as constructing mental experience from sensory stimulation. And we know a lot about, well, a lot may be a bit conceited for the field, but we know something about the mechanisms that enable us at various different stages to pick up information, to integrate, so picking up with our external receptors, picking up features, integrating these features into objects, placing objects into contexts and scenes, and creating out of these episodes. So we kind of have this notion of constructing our mental experience from the outside in, but we know, and I know that a lot of you also share this view, that this is only part of what goes on, and really what also happens is that the traces of our experience at many, many different time constants, from these brief, iconic traces from working memory and from our long-term memories, including our long-term memories, sort of remote memories, all worked back in a predictive and prospective, proactive fashion in order to guide the perception. And I think you can't really put it more elegantly or more succinctly than Helmholtz, who said, early on in his treatise of optics, that reminiscences of our previous experiences act in conjunction with the present sensations in order to produce a perceptual image. And basically that's, it's taken us a long, sometimes we forget some of the big ideas. Of course, there are lots of big ideas out there. Many of them contradict one another. But it sometimes takes a long time before we're actually able to start testing these out and sort of creating the right tasks and parameters and methods with which we can see whether this is really the case and watch it unfolding. So this is some of what I want to talk to you about today. But I wanted to just step a bit back just to have some fun. I know that many of my colleagues who study perception or attention or memory know some of these things, but I think it's always good to take stock of some of the basics, and also everybody thinks about the basics in a slightly different way, so maybe you get exposed to my quirky way of thinking about the basics. So if we were to think about the nature of perception, we can think about it in two ways. We can think about it in our everyday experience of it, in our subjective phenomenological experience of it, or we can think of it in terms of the ecological validity of perception. And when we introspect on our mental experience, we kind of think of, if we think of like what our experience is about, we might think like, well, what would life be without this? It all doesn't make any sense, and we kind of need to have some kind of mental life to make sense out of our existence, and it must be there for our musing and our wonderment. And we think that we actually perceive everything. We sense everything. The world around us is all at our senses. It's boundless, veridical, reactive to the incoming stimulation, and that it kind of lives in the present moment. when we try to test people and test what they can pick up from the world and what they can discriminate and what they react to, we find a really different picture, which I think speaks to the ecological validity of perception. What we find is that our perception is really incomplete, and when everything works really well, it's selective, in a good way, focused, adaptive, and very proactive, so not something that's just reactive and in the present, but also anticipating in the future. And that is the kind of perception we need if we're not just going to think about the universe, but kind of try to behave and act and manipulate and do things within it. So I have to say that, the science that I'm going to talk about speaks to this second aspect of perception, this ecological validity view of perception, but of course that doesn't mean we don't have the other phenomenology of it. And actually how to marry these two sides of perception is something that I'm going to leave to Leon and Ron here, who think about things like consciousness and stuff. Okay, so then we enter this, if we accept this idea of the ecological perspective of perception, we then have to try to understand, like, what is it that limits our perception? And just because we have a bit of time and because this is supposed to be more of an open public lecture, I thought we could go through some nice demonstrations, some of which I'm sure many of you have seen before. So our perception is limited. So here's a really example that I really like that I found on Google one of these days.
To test just how much attention the attention-stealing design of the new Skoda Fabia actually steals, we left one parked on this ordinary road in West London. We wanted to see if its sharp crystalline shapes, bold lines, and lower, wider profile would attract the desired level of attention. Will the 17-inch black alloy wheels stop passers-by in their tracks? Will the angular headlights attract the attention of other road users? Will a crowd gather to check out its fresh, sporty look? Well, not quite. But did the attention-stealing design distract you from noticing that the entire street has been changing right before your very eyes? Don't believe us? Have another look. Did you spot the van changing to a taxi? How about the scooter changing to a pair of bicycles? Or the lady holding a pig? Let alone the fact that the entire street is now completely different. Didn't think so. So there we have it.
Okay, so I think this is a particularly nice illustration of it. But obviously, the skeptics among us say, that's cheating. That's not perception. These things go away. They're in intervals, intermissions. It's really about forgetting and not being able to sort of have the memory to bridge to the next thing. So then we have the classic.
The monkey business illusion. Count how many times the players wearing white pass the ball. The correct answer is 16 passes. Did you spot the gorilla? For people who haven't seen or heard about a video like this before, about half miss the gorilla. If you knew about the gorilla, you probably saw it. But did you notice the curtain changing color or the player on the black team leaving the game? Let's rewind and watch it again. Here comes the gorilla, and there goes a player, and the curtain is changing from red to gold. When you're looking for a gorilla, you often miss other unexpected events.
Okay, so that's quite a nice demonstration, and this also makes, so how many of you hadn't seen the gorilla before, or hadn't seen the video before? Anybody, or does anyone miss the gorilla? And this actually makes this the other counterpoint, which is the point of this lecture, which is that I'm sure all of you saw the gorilla because you knew the gorilla was there, and you had a memory for having seen this video, which was a memory in the past that probably made your goal not counting the basketball passes, but waiting for that gorilla. So how many of you actually managed to screw up counting the passes just because you were waiting for the gorilla? I bet a bunch of you did that. So that is a lot of the points of also what I want to tell you about today. But I would argue that the limitation in our perception is really severe. And so first we see, okay, we don't need these interruptions. This can happen also in a continuous scene. I mean, especially if you've missed the gorilla in the past, as I did when I first saw this video, when Dan Simons came and gave a talk at Oxford many, many years ago. But also it can happen when the stimulus is very impoverished. So, this is like Dan Simons
that's the monkey business
advertisement
illusion
for himself. So sometimes even when you have only one object on the screen, and not a very complicated object, but if you have these ambiguous figures that have multiple interpretations, like this one that Wittgenstein wrote about, it was an illustration in a German newspaper, you can see the rabbit or the duck, but you cannot see the rabbit duck or the drabbit. You see one or the other at any moment in time in your head. So of course there are many such illustrations. There's the Rubens vase. There's the most irritating for me, the Necker cube, because I'm always trying to push it to the other direction. It's really hard to do. So in this case, even when we have just simple objects, the brain has to settle on one representation at a time. And sometimes we see all these displays and anecdotes or illustrations, but still all of this doesn't shake sort of that strong phenomenological or subjective phenomenology sense that we have, that actually if only things were, for me it's okay, I can actually perceive everything at a given time. And that creates a real problem, because I think especially people who are not scientists and not psychologists, they don't take the limitations of perception very seriously. So sometimes when there are situations in which mistakes can be made, people emphasize people actually making the wrong decisions, weighing the evidence incorrectly, but they don't actually emphasize the fact that maybe people aren't perceiving some of the things in the first place. So I think the limits of perception are real. They're not taken seriously, for example, in our educational systems, when we have kids in very crowded classroom situations where kids aren't really taking in all of the things that they have to know. And it would be, it would be of great advantage if we actually could accept these and sort of therefore design interfaces, context, situations, procedures with this in mind. So I want to show you sort of some study that we've done in the lab with some colleagues who are from anesthesiology, where they were interested in testing whether some of these perceptual effects actually cause errors in medical surgery rooms. And in fact, medical errors is like something like the biggest cause of death after heart attacks, and so it's like number 3 or 4 in the world. So they were interested in testing, first of all, whether medics actually also have missed things like the gorilla, or they are somehow, as they believe they are, gods and they can do everything. And also whether that applies also in clinically relevant contexts. So we actually did a study where we took people who were used to doing training, resuscitation training, and we did we had a video of a resuscitation training in which we introduced several changes, like either change blindness or inattentional blindness. And we had either young medical students, highly expert anesthesiologists, or people who actually deliver this resuscitation course watch these videos, and we ask them to watch the video and to see if all the procedures are being followed correctly and to comment on them, and then we ask them, we debrief them at the end about whether they saw certain changes. So it's about 8 seconds, so I'll just show you. It's a very boring video, but maybe not if you're a resuscitation trainee, but
27, 28, 29, 30.
Okay, that's 2 minutes. Can we do a rhythm check? That's a shockable rhythm. Rosie, can I hand over to you, please?
Okay, Martin, can you give me chest protections, please? We're going to charge on the test. Alex, get rid of the oxygen, please. Okay, charging at 150. Okay, Martin, stand back, please. Rocky, 150, everybody clear. Back in the test, please continue giving oxygen.
Rosie, can I see your adrenaline?
Okay, so maybe some of you saw some funky things going on, or maybe not. So we debriefed people, and we had some foil questions of things that didn't happen, stuff, so that we could keep them on their toes. And we asked them what are the things that they perceived here. And there were a bunch of changes that were introduced. There were, in this case, 5 changes. Some of them didn't matter at all. I mean, they were kind of obvious changes, but it wouldn't have had any consequence to the person who's being resuscitated. So, for example, the color of the hat changed, or the stethoscope changed, or the person, the individual who's delivering the resuscitation changes. So all of that, were obvious changes, but they wouldn't have affected the person's lives. But some of them, for example, the thing that is used for intubating the person changed, and actually the oxygen just disconnected, which actually if it had happened, and this was it just happened, it wasn't there was no cut out or anything, it just happens during the thing, and it actually made a sound, and if that actually were to happen, that would have killed the person. So these here are the percentages of people who noticed, who said yes, that they saw these changes, and the first ones are the medical students, the next ones are the trained anesthesiologists, and the third one are the highly expert people who deliver the training course. So there are 2 sides to this. One is there's some reassurance that experience does, with the relevant things, experience does help. So some of the doctors actually noticed that the oxygen disconnected. But the bad news is only less than a quarter of the doctors noticed that the oxygen tube got disconnected. So, this is just to show that our limits in perception, are things that matter in these kind of contexts where there are lots of things going on, many of which are relevant. And then you might say, well, there's a video, that's not how in real life people do. So Paul Grieg, who was an anesthesiologist, at that time was doing his PhD between us and anesthesiology, has actually also been doing these things in the real, in situ, with looking with eye trackers of people. And these guys here, who are the people who work in this specific training, anesthesiology, resuscitation training, they've kind of become sort of cinema actors and stooges. So they actually, now they go on, they change their clothes, they come back, they connect things and stuff. So they actually have this whole scenario that they play out in real 4-dimensional life. And then we can measure whether people also miss things when they're immersed in these environments. And again, there's 2 sides of the story. People do much better in immersive environments, but they actually really do really badly if you're thinking about your life being on the line as that patient. So the limits of perception matter, and we should consider them when we think about designing things in the world. But I would say that it's not that our perception is bad. Our perception is selective, and it's designed for particular purposes. So if I give you an impossible task, and if I just ask you, do the following scenes contain a car? Oops. Did you feel like you could do that? You probably felt like you could do this. This is crazy. I mean, you had no template of what the car is going to look like, the size, the color, the shape, where it's going to show up. These things are flickering by in a moment. So it's not that, that our perception is bad. It's our perception is selective and focused. And once you have a goal and you know what you're looking for, you're phenomenally amazing at doing this. So it's these two sides. It's just about the nature of our perception rather about the quality of it being positive or negative or bad or good. So we have to admit that our perception has some quirky limitations, but then we say, why? Why does it have limitations? And then you kind of enter sort of the thinking of the field of attention, which has these very sophisticated ideas of why perception is limited, which is like, well, it has limited capacity. It has finite resources. There's some kind of bottleneck. Oh, well, that doesn't explain anything, does it? I mean, it's just restating the problem. These are vacuous explanations, like, oh, there's too much load. It's like, what does that mean? You know, it's like, is it the case that, you know, we just have like a bucket of tension and we have to kind of dish it out and you run out of things if there's too many things? Probably not. Or there's some kind of currency that you run out in the brain. So I think the better way to think about it, and this is not a solution, it's just a direction of thinking about it, is actually to think about not as our perception as having, you know, limited capacity or having too much load, is actually to try to understand what the principles of organization of our sensory motor systems are, that and what kind of challenges they pose for perception. So we know, for example, that we have in the sensory systems these highly distributed networks of areas with relative functional specialization. There's a lot of concurrent processing, so that actually information is distributed about the color and the motion and what kind of motion and the luminance and the contours, which ultimately all has to be put back together. Even if we focus on one of these areas, so for example, if we focus on arbitrary area, inferior temporal cortex, IT, within that area, you have a whole ensemble of neurons, and the information is distributed across these ensembles of neurons. And even when we look, and again, you need to integrate somehow and get some sense out of this population-level code of what's going on. And then even if we look further more granularly into an individual cell, we see that cells, for example, in these areas that are late in the loose hierarchy of the visual system, have these large receptive fields where many things will impact on that receptive field. So what's that cell gonna, what it reports, what is it reporting? Some kind of average of fruit, or, you know, like how do you then get information about anything specific in any of these areas that you can put together into a coherent structure? So I would say that, you know, the real challenges of perception is the fact that we have concurrent processing in networks, we have distributed processing in these networks and in ensembles of neurons, and all of this requires a lot of prioritization, selection, and integration. We also obviously have the problem that these are biological units which might be noisy, and it is true that we probably also have some kind of overall, sometime kind of need to maintain things in some kind of check of excitation and inhibition. So there may be some homeostatic elements as well. So how do we solve this problem? So here the field of attention says, oh, we solved this problem. This is like the problem of attention. It's all about being able to prioritize and select things in order to simplify the integration of these objects. And once you start selecting and prioritizing, then the mutual influences of those things can reinforce one another, and it starts like a virtuous cycle. So we have this idea in perception that we have natural intrinsic biases that occur of things that evolution has kind of built into the system to prioritize certain things like loud, bright, fast, transient things might kind of themselves have an edge in the perceptual competition. But, and I think this is a more interesting part of attention, we are also able to exert sort of top-down biases according, in the field, primarily recognize our goals. And we have these, and we know a lot about these, okay, so the way this would work, for example, is rather than kind of being confronted with like a given cell, rather than being confronted with a whole like fruit salad here, we'll be able to focus on a specific location or focus on features to object-related features in order to integrate certain objects, and that greatly simplifies the problem of binding the information back together. So we know a lot about a lot of these mechanisms through attention research. So for example, we know that we have a large-scale network of areas, which originally proposed by Marcel Mesulam in early 80s, which now has been vindicated by MR, initially the first studies by Corbetta, but then like we sort of showed it for the first time in the single human and showed that this has a close bearing to the ocular motor system. And this network is able to sort of move spatial biases around. We know from work, like for example, starting from work from Hilliard using ERPs, that you get a differential quality of processing of sensory stimuli in the brain, depending on whether something is important or not important, attended or unattended. The assumption has been that these networks influence these sensory systems, and we can show this by combining TMS with recordings in humans or microstimulation with single units in monkeys like Tyrone Moore has done. And we can also see the brain in this moment of expectation. And last time I spoke a lot about changes in oscillatory patterns of activity like alpha changing and becoming less over areas of the cortex that are receptive to relevant information. So we have these desynchronization of alpha, or these blue patches, according to expectation and relevance of stimuli. And we can also watch the stimulus, so the brain pre-activate the templates of the items that are attended, that are expected. And this is pretty much the textbook view of attention now, I would say, still nowadays. And as Leon said, you know, for a long time it was very much focused on sort of spatial attention and also object-based attention. And you know, we've learned a lot at the human, but also at the circuit and the cellular level across the whole field to understand some of these mechanisms. And this is a fantastic start, but it is really only a start. So some of what I want to talk about today is that there are two fundamental things missing here, is that the type of memories that are in the attention theories are very limited. So attention is really very amnesic, working only with these short-term goal-based, goal-related top-down signals. And also that the whole picture is very static, and as if all you get is like this snapshot of the brain in this like snapshot anticipation system, and it doesn't take into account the evolving temporal structures of events. So I've chosen to just show you like 3 examples, something from a short-term memory, something from a kind of a middle-term memory, and some stuff from long-term memory, just to show, trying to illustrate how all of these memories are constantly sort of influencing our pickup of information from the world. So I'll just start with some of the working memory stuff. So last time I did speak a lot about how working memory itself is very selective and codes informative features, and it's also prospective in nature. So I'm going to show you a different study that also shows its prospective and dynamic nature, taking temporal structures into account. So this was a study that was done by Nick Myers when he was a graduate student in the lab between me and Mark Stokes. And it's a very simple study, so people just have to, they get a template in the beginning of a block, which is just an oriented bar. So this is, every person got 8 orientations in random order out of a possible 16 in different blocks. And in this case, every time the person sees this orientation, they then that's the target, and they have to press a button. This happens 1 out of every 16 stimuli in random order. And this task has a certain tempo, so it's more or less every 600 milliseconds that these stimuli are occurring. People can do this, they're not perfect, but you can see that they detect the target, they make some false alarms to things that look like the targets, and you get this nice behavioral tuning curve. In this task, we were then recording MEG, so magnetic encephalography. And we can then do things that when I started off, whenever, I don't too long ago to remember, in the 80s, doing this kind of stuff was just absolutely amazing to think of. Because back then, you could get average responses only across a group of people. And now what we can do is we can actually we can decode what stimulus orientation someone is looking at on the screen just by the pattern, the mapping of the voltage, or in this case, the magnetic field associated with the voltage changes on the scalp. So we have like a scalp topography that's associated with a given feature, and we can see that that if you train on that orientation and then test another set of stimuli with the same orientation, you get really good match, and the orientations that are nearby kind of fall off, and you get this tuning curve, which is associated with how well the map over the head maps to the stimulus on the screen. So amazing stuff that you could never ever dream of doing when I started off. And with these nice methods, what we can do is we can first of all decode what stimulus orientation is the person looking at the screen. And we can do that really well, so within about 50 milliseconds or so, boom, the response flashes up and remains up. And you can see that most of the activity is concentrated over the back of the head in MEG. And that is beautiful and exciting, but it's something that we already know happens. Brain processes visual stimuli with some kind of specificity. But we can also decode what's not being presented on the screen, but what is the template that people have in memory, and they're having to match the stimuli, that incoming stimuli against. And here, if we follow the normal standard theory of attention, what we would expect is like, okay, it'll be a miracle if we can see anything at all with these methods, but if we can see anything at all, what we should see is that the brain is holding on to that template, and this delay activity is just tonic and just stays rumbling on there, and whenever a stimulus comes in, happens to match it, it gives that a boost, great, and then if it doesn't match, it doesn't get a boost, but you'd expect this kind of tonic elevation of delay activity. And that is not at all what we saw. So what we saw is that the brain picks up also temporal information, and it turns on and off this template in the tempo of the task in order to anticipate just before the incoming of the stimuli, to sort of pre-activate this template, so a little bit before the average time of the stimulus, so that when the stimulus happens, you're in this good state. So you have this highly dynamic use of these short-term working memory templates that are going in and out to help you guide your perceptual functions. So we published this paper, and then we left out one bit of it, which is we also in the task we left out some blanks. So we had some stimuli were just skipped, so 1 out of 16 stimuli, so we just skipped them. We had these omissions, and this is noisy data, so we haven't replicated this, although in these tasks people came for 2 sessions, they did like thousands of trials, so these are, but there are very few omission trials, so we don't have as much data in the omission trials. But what we see is even when nothing is presented on the screen, but the person's anticipating something to be presented on the screen more or less at that time, you can here see that the brain turns on this template in anticipation, expecting this thing to come, and then nothing happens. So these short-term traces then, we know this from the attention literature anyway, they're doing some heavy lifting in terms of guiding perception, but unlike the theories of attention that are mainly out there, these things are also carrying, automatically, and there's no instructions about this, it's carrying some of the tempo or the dynamics of the task. So then I want to sort of show another example. This is work that's still ongoing and still being analyzed, which is that in-between time when, I think I know that some of you guys think about it with adaptation, with the SSA and things like that. It's like this, the time course of things that are happening over seconds and times and over multiple items in a context, for example. So if we think of these as contextual probabilities, we also tend to think about it as a hazard rate, so the temporal conditional probability of things happening given that they haven't happened already. And here as well we can see this work of prospective memories or extraction of these traces or integration of information over these relatively short time courses. So this is a task that's been run by André Cravo. André was he came as a visiting student to the lab from Brazil, from São Paulo, and he went back. He got a job, he set up his lab, and then he came back just to visit for a year because nobody ever really leaves my lab. So he was back and, for a few months, and he ran this experiment, which we're still analyzing. So in this task, it's very simple. Basically, all people have to do is detect a grating, which is either horizontal or vertical, and this grating appears among a bunch of noise patches just to make it sensorially very difficult to detect. And it can happen after 1.5 seconds, 2.5 seconds, or 3.5 seconds. And that's it. So the only other trick is that the probability of when it happens changes in different blocks. So in some blocks, there's a very low probability that it happens at 1.5 seconds, and then the probability goes up. So it's like 10% probability, and then it goes up to 45. We also have some catch trials, so overall it's like 8% probability of it happening. Then you have other blocks where there's a high probability of it happening early, then low, and then high again. Okay, so that's it, and except that time is weird. So time is weird, so that means that you have very different probabilities at the first event, but given that something hasn't happened, the likelihood that it will happen again changes, so you have the cumulative probability or the hazard rate changes like this, so you have a big difference in probabilities in the beginning, but then once it's passed, then the probabilities kind of become similar. You have cumulative probabilities becoming similar. And basically, again, if you ask people, they don't have any idea about these probabilities being manipulated, but their behavior betrays that their brain has picked up on these things, so they're faster and they're more accurate when the probability of the events is high than when it's low. And once, like with the passage of time, things don't matter so much anymore, then behavior kind of becomes equated after that. And unfortunately, we don't have much to show you on the brain side because this is still really being analyzed, and we've been doing some decoding and all kinds of fancy things. So now we just have some ERFs, or event-related fields, where you can see here as well that the fields elicited by those targets are modulated significantly, even the early sensory components, when according to these probabilities of events happening. So this is like the brain extracting temporal regularities of things in sort of context and using these to guide perception. And this is just to show where the effects are, again, in some of these sensory areas. Then we move into like the real long-term memory as we like to think about it, or contextual associations. And some of the beautiful work, comes from like the lab of people like Moshe Bar, who talked about contextual priming. And he likes to talk about, how a ambiguous stimulus might get a really different interpretation of, as if it occurs within a workshop or within a bathroom. So here you have a drill or a hairdryer. But there are also other groups. I particularly like also the work of Marvin Chun, showing the effects of learned context in sort of guiding perception or guiding behavior. So in these tasks, people have to identify a target. In this case is this T, which occur among distractors. And in general, people get a bit better at doing this over time, just because they get used to the task. But if this particular pattern of distractors is repeated, then people's reaction times are even better. So they have this kind of contextual memory, which is aiding them. And again, if you ask people, according to the Chun work, this is completely implicit, and people don't have awareness, and they can't recognize which of these are old versus new contexts that are repeated. So we wanted to study this phenomenon of long-term memories guiding perception, but we also wanted to do it in a way where we could isolate the orienting of attention from long-term memories and the modulation of perception. And in these kinds of tasks, you can't do that because everything is happening at the same time. People are learning the associations, they're orienting attention, they're selecting the target all in one frame or one screen. And so there's all these multiple functions that are taking place at the same time. So we basically decomposed or took apart some of the ideas of this task and kind of did some learning in a separate phase and then testing how these memories could orient attention separately. So in our tasks, the first thing that people do is they learn a bunch of new arbitrary associations. So I'm showing you some completely made up examples just from actually my own sort of memories with very big exaggerated targets. In the real tasks, it's really hard. You wouldn't be able to see it until you really explored and looked around. But people get, for example, in most of our tasks, they have to detect a key that's embedded within a context. And once they do that, they click a mouse, they click on this thing, they move on, and then they do that in another scene. You can see my life going by here. And then they click. And then they, oh my God, I can't see this. And then finally get to Oxford. Okay, so we teach people, depending on the task, 100, 200, 250 of these. People are really good. You can usually, if you present these things about 5 times, people are not really at ceiling at this. And then typically we just send them home, filled with new, useless memories, except for the next day we bring them back and we test whether those scenes without the target in it, if we present them to them briefly, whether they can then facilitate performance. So you'd come back to the lab and you might have something like that. And you have to, in this case, just see whether the key was presented in the second time or not. And we've done this a gazillion ways. So I'm just showing you one of our experiments just to show you some of the brain data. So we've done this. This works amazingly well. It's like the effects are huge. It works with 50 millisecond intervals. It's super fast. It's like really a really, really robust phenomenon. This is like the worst kind of illustration that I can make, because we adapted this for doing MRI. So we actually presented the scenes for a really long time and varied time so we could isolate the activity related to these memory cues. And then we had an ISI, and then we presented the target. And there's nothing inherent in these scenes other than the association of the target with them. So obviously everything is counterbalanced. So some scenes for some people mean cue left, others cue right, others valid or neutral or invalid. So everything is counterbalanced. And we see that in these kinds of tasks, even with these really slow parameters, but also with really fast parameters, your reaction times are much faster, but also your sensitivity, your perceptual pickup, your perceptual sensitivity like D prime is vastly improved by having things appear at a place where you've previously learned them to be. And when we look at the brain, we see the old faithful frontal parietal network being involved in this task, but we also kick in memory-related areas like the hippocampus. And this study is actually a replication of a previous study by Jen Summerfield, where we saw that the hippocampus activity actually correlates on a trial-by-trial basis with the behavioral benefit that people have on that trial. So you get like these memory areas and this dorsal spatial attention network working together, and because we have this really long interval, we can also see this preparation of visual excitability in the visual areas, changing receptivity for the location of the target to come. So this is the unfolded sort of back of the head, kind of covering some of the visual areas, and you can see that there's a biasing where you get relative enhancement of activity in the area contralateral to the expected stimulus, and the other way around in the ipsilateral area. And we've also shown this change in excitability also with EEG, for example, looking at alpha changes. And we also see that these changes also have an impact on the early visual response with ERPs. So these long-term memories, they can also change excitability in sensory areas. They have anticipatory effects. They have a consequence for early visual processing and obviously they affect behavior. So I remember when I was doing this, I kind of got a bit worried, and I thought, if memory plays such a big role in guiding our behaviors and our perception, that's kind of bad news. Like if our memories start failing, for example, as we get older, our memories, certainly my memory, gets a little bit worse and more rusty. It's also true, obviously, in some of the neurodegenerative conditions. And if this is playing a big part in our perception, maybe some of the problems that are associated in aging and in neurodegeneration may actually be influencing even our very earliest pickup of information through sensory processing. So we actually ran a version of this study with elder participants or older participants, and by now some time has passed and the experiments have become a bit more fun and they kind of keep evolving over time. And in this case, people had not just to look for a key, but they were shown an object. That object was then embedded in a scene. They had to find that object in the scene, and then they learned. And we compared a group of younger, 20 to 40, to older, 60 to 80, more or less, year-olds. And we saw that people were really good at doing the task, so we gave them a lot of time to find the object initially. So even at the beginning, even this looks really bad, but actually this is like 98% accuracy. So people are really accurate at this. And everybody learns by the end. Young and old people are at the same level. People get faster and faster at doing this. The older people are a bit slower, but they're also learning with the same slope. And so the learning thing is fine. We're a little bit slower, take a moment longer to get there, but they all learn. And then we first of all can test the memory, the quality of the memory. And first we need to see if memories are affected in aging. So we have this task where people are presented with the scene, and then they're first told, like, okay, place the cursor where you think the object was, and they give a confidence rating. Then they have to select which object it was that was in the scene, and then they give a confidence rating. So we can test the spatial memory and the object memory, and we see that indeed, as the literature has shown before, older participants are impaired at this task relative to the younger participants. So they have significant impairments both in the spatial location of items and the object identified in these items. So then the question is, what happens with attention? Is it also impaired? So I thought for sure, yes, I'm a pessimist. I think things are always downhill and terrible. So here we bring people back for a next session. We present them just with a scene. And then the item appears or doesn't appear, and then they have to just respond to it. So it's really easy. It's just a reaction time. We didn't do the perceptual discrimination one. We just kept it really simple. And actually, what we find is that so here these items appear either in the remembered or in another location. And what we see is that for both young and older people, even though the reaction times of older people are slower, they have the same amount of benefit from these memory cues as younger participants. So actually it's a 9% benefit in this case, in this task, for both the young participants and the older participants. So this suggests that even though there is a problem with older people having conscious access to retrieval of those memories or some other memories that exist in parallel are still there, and they are still changing and guiding your perception and behavior. So this shows that these are really robust effects. Even when you can't access them consciously, your brain is still utilizing those memories to guide perception. In young people, there is a very strong correlation between the quality of their memory and the benefits that they get from these cues. People remember things well, they have a good cueing effect, and that's really highly correlated. In older people, that correlation breaks down completely. So they have problems accessing it consciously, but they don't have any problems utilizing these memories behaviorally. So that's good news, and it shows how robustly memories influence your perception, even when it doesn't work for memory's sake. It works for perception's sake. So the last study then is this. We've also done this kind of experiment, seeing whether our memories are, again, not only able to learn these associations but statically, but whether they can also sort of maintain some of the dynamic associations that are relevant, that might be useful to guide behavior, again, and to guide perception at the right time. And this was again done by Andrea, but this time when he was still a student in the lab. So in this experiment, what we did is the same kind of idea. So people see a scene, then there's a target that occurs within this scene. Andrea and Gustavo, who was another student in the lab, they decided they wanted to have something kind of evocative, like a little bomb that gets activated, and people had to learn to deactivate the bomb really quickly or else it'd blow up. And the bomb either happened early or late. So it's very simple. And so this is highly delayed because of PowerPoint, but so we have things like the bomb activates soon, or you get the situation where it activates late. This is exaggerated, so the real task doesn't feel quite so different like that. And we just got people to learn this task. I mean, as far as we could tell, we couldn't. Obviously, people have studied, timing and things. We didn't find any task in the literature that has specifically looked at temporal contextual associations and learning of these particular intervals. A lot of people study what order things happen in what sequence and stuff, but just kind of learning of an interval is something in this kind of contextual learning is something that's not very prevalent. And actually, if you guys know about some of that stuff, I'd love to hear about it, because we've kind of, sometimes, you have to look in some completely other literature. Everything is called something different, and we might not have run into it. But the first thing that we had to show is that people can learn these associations. So first of all, they do get fast. We did it in 2 blocks, so we kind of trained them a lot. So they get faster and faster, and then they did another block. They continue being faster and faster. We asked them explicitly after the first block or the second. They have good accuracy, really good by the end of what time the target happens. And then we ask, if we then send them away, bring them back, and use these scenes and then present things at the right or the wrong time, does that change their performance? And of course the answer is yes, or else I wouldn't be telling you this. So if we have things happening 25% of the time in the wrong timing, they are slower, so they're much faster if it happens at the right time than at the wrong time. And they're also, again, they have better perceptual discrimination or D prime for things occurring at the valid location than the invalid location. So when time is relevant, I'm not sure that this happens always, but when timing or the temporal association is relevant in memories, these temporal associations somehow are preserved and can guide behavior in the future. And of course, as we like to do all the time, we can look under the hood and we see here sort of when this is during the orienting task, so we have the scene, and then the placeholder occurs, and then the bomb gets activated, and we can see, we can record like the standard potential, which records sort of preparation or anticipation of stimuli. We can see that it's modulated according to the temporal expectation. Even when you just see a scene, even before the placeholder happens, these things already start diverging. So this potential, which is known as the contingent negative variation, starts going down more steeply if you're anticipating the target to happen early, which would be at this time here, compared to if you're anticipating the target late, which would be much later over here. So you see that there's this huge CNV effect, and that effect is highly correlated with performance benefits as well. So the quality of the memory correlates with reaction time, it correlates with the depth of the CNV, and the CNV also correlates with the behavioral effects. So our memories are basically dishing out information which is kind of meeting the incoming sensory stimulation. It does that all the time. It does that even when the memories don't work very well for memory's sake. It can be dynamic and actually prepare things to anticipate things in moments in time. So that was the full spectrum. So just to sort of conclude then, hopefully this makes us think about these 2 monoliths or pillars of cognition as working much more closely integrated together. So to conclude, just to thank my wonderful lab and all the funding sources, and to thank you for listening on a rainy day. Thank you.